Hey kids, welcome to the final episode of Programming TwinCAT with Jeremy. In this episode, I'm going to show you guys, I'm going to walk you through this alternative practical test that we're doing this week. But before I get started with that, I just want to go over how to get some screenshots from TwinCAT 3 running in the virtual machine because it's a little confusing, and I can see from a lot of the lab reports I've been getting that some of you have been struggling with it. Okay, so I'm going to show you how I do it. There's many different ways to do this, but I think this is a good way. So for starters, what I do is I create a new Word document, and I put a title page in that document. So there's my title page, and next I just put some headings in. So I have placeholders reminding me what I need to copy and paste into the lab report. Okay, now I've got a program open here called Snip and Sketch, which is included in Windows 10. There's another one called Snipping Tool, but this is the one Microsoft wants you to use now. And I don't need to have this open, but the reason I have it open is just to note what it says in the middle here. So if you press Windows logo key plus Shift and S at the same time, you will do a snip. That will initiate a snip. Okay, so again, we don't need to have this open. All right, so I'm going to close it. Now, where this can get confusing is that we're running a Windows virtual machine, and we're also running Windows, or I'm running Windows on my computer. So let's go to the virtual machine. Okay, so I'm in VirtualBox right now, and the easiest way to do this is going to be to have a shared clipboard between your virtual machine and your real physical computer. Now, to do this, the first thing you need to do is install the guest editions. Now, I went through that in the Lab 9 video right at the beginning, how to install the guest editions so that you can make your screen fit into your widescreen monitor. Your VirtualBox screen will be as wide as your monitor. So it's the same thing. If you've already done that, you don't need to do it again. Guest editions is installed and you're good to go. But the next step is to enable the shared clipboard. Now, to do that, on the virtual machine itself, you're going to go to Devices, and here we've got Shared Clipboard, and you'll probably find that it's disabled. Now, I'm only going to want to copy paste things from the VM into my my regular computer. So I could just choose to go from the guest, which is my virtual machine, to the host, but what the heck, I'm going to make it bidirectional. So that'll mean I can copy and paste between both of them. So if I just enable that, now I've got a shared clipboard between both systems, because Word is running on my regular computer and TwinCAT 3 is running in my virtual machine. So I'm in the virtual machine right now, and I click that hotkey combination of Win Shift S and see what happens. Now I know that I have this is happening in the virtual machine because only the virtual machine has become gray. The top menu there, see how it's not gray up here, and the bottom bar, start bar, is not gray at all. So I'm in the VM right now. And now I just have to left click and drag with my mouse to put a rectangle around the area that I want to copy. So let's say I want to copy that. All right, so I let go of the button, and now it's going to say done. All right, so that's kind of hidden, but it's telling me that the snip was saved to the clipboard, and now I've shared my clipboard. All right, so now I can go back to Word. Let's get out of here, go back to Word. All right, and I would be pasting that particular thing under motor control. So the hotkey for that is Control V, or you can right click and choose paste. That should work as well. And you'd paste, there you go, keep source formatting. Right? And there it is. Easy peasy lemon squeezy. Now, if you don't want to install the, did I just say that? Something my kids say. Sorry. If you don't want to install the guest edition CD in your virtual machine, you can also use the snipping tool that is on your regular Windows. But to do that is a little bit more difficult. So once you're clicked into the VM, you'll have to sort of get out of the VM. Now, the default key to do that assuming you haven't changed it, is the right control key. So I'm going to press the right control key. I just did. And now if I do Win-Shift-S, now the snipping tool on my computer has become activated, and I can just do the same thing. You can see it's paused, even the video is paused there. So I'll select the area again. All right, let go, and boom. Okay, I copied it. I'm wondering what that's going to look like on the video. And now I'll go back to Word, and I'll paste it in. So enter here, I'll put right there. All right, so I circled the same area there. I guess you guys couldn't really see that, but I rectangled the same area. It's easier if you use the shared clipboard, but either way will work. All right, so let's go away from that. So last thing, some people are saying to me, oh, I can't save my Word document to a PDF. Okay, here's how you do that. So if you go to File, Save As, all right, and you're going to choose where you want to save it. Now the key is right here on the drop down. You will definitely have this option of PDF. You just choose PDF, and when you save it, it'll save it as a PDF. All right, easy as that. Although, to be honest, it's not a big deal if you upload a Word document. But this is a good thing to know just for the future anyway. All right, that's enough talking about that stuff. So I'm going to lower that. And now let's start talking about this practical test. Now, the practical test is not a practical test like you are used to, right? We can't be in the lab. Nobody's watching what you're doing. So it's we'll say test in quotes. It's essentially just another lab activity. In fact, originally it was going to be lab 10, but Warren and I thought, well, what's the point of throwing another different lab test out there? So let's make lab 10 into the lab test. So that's what we did. And there's the goals of this lab test are maybe different than what you're expecting as well. For one thing, this lab test is not going to be about testing your ability to devise ladder logic. The goal of this lab test is to test whether you are able to implement ladder logic and an HMI visualization in TwinCAT. That's it. So the things we've done in the last two labs, we're just doing it again. It's a little more complicated this time, but all the information should be there for you to succeed. And if not, you can ask me for some help, right? So shoot me an email and I'll try to give you a hand. Okay. The other goals of this lab test are to essentially take up assignment number 2, because this is very much based on assignment number 2. And I want to make sure that everybody fully understands how the ladder logic and the control for the bidirectional motor works. All right, so this is essentially implementing assignment 2 in TwinCAT 3. And we're also going to do a new technique of implementing a motor simulation in the PLC logic. All right, and I'll talk a bit more about that when we get there. And then the third part will be making an HMI visualization that allows us to see how the motor really works, which will hopefully, again, sort of drive home any misunderstanding that you might have about how the motor control works and how the motor will react to the commands from the PLC. All right, so let's get started looking through this. Okay, I'm going to go back to my virtual machine. I'm going to try to go back to my virtual machine. There we go. All right, so I'm back at the VM. All right, so the first thing you're going to do if you're following the instructions is you're going to, make this whole project and, of course, do the configuration that we did on the first lab in detail. So that's going to be under this real time, right? We're going to read from the target. We're going to make sure this one is selected as the isolated. All right, and then we'll set it and move on. Close it and never think about it again. You may also run into a licensing error, in which case you're going to click this 7-day trial license, type in whatever it has there, 9A, all right, and click OK. And that generates another 7-day trial license for TwinCAT 3. So if you get an error saying you have no license, that's it. You can do that indefinitely as many times as you want, and no problem. All right, so let's close that down. So we've created our new PLC project, and you can look back at the lab aid instructions if you forget how to do this. Okay, next thing we're going to do is create some variables. Now the lab instructions are going to tell you to just create the first 13 variables here to begin, because these are the first 13 variables that are related to the control of the motor. Now, how did I come up with these things? So recall from, let's see, I'm going to shift again here to the lab instructions. Okay, so scroll down. There's quite a few words in this instructions. I hope they're useful. Give them a read. But here we go. Here's the assignment 2 instructions. All right, and if we scroll down, here we go. Here is the diagram from the assignment 2. All right, so what I'm going to do here is I'm actually just going to take a little screenshot of this so I can annotate it for you. So I'm going to zoom in a bit. And I'm actually going to screenshot with a different program I like to use called GreenShot. So you'll see what that looks like. All right, I'll take a screenshot here. All right, and I'm going to open that in my image editor. GreenShot's a nifty program. If you want to install something and you don't like the snipping tool or the snipping grip or snipping whatever it is, this is a bit more powerful tool because it has some editing stuff here that I like to use. Okay, so the assignment 2 instructions were to take this hardwired control of a bidirectional 3-phase motor here and change it to a PLC control. And the instructions suggested that the first thing you might want to do is just circle all the I/O points. Okay, so let's start with that. So I'm going to start off by showing you all the inputs to the PLC. All right, so the first one we're going to talk about is the forward push button. That'll be a momentary push button, all right, to start motor direction moving in the forward direction. We've got our stop push button here, and you can see that's a normally closed push button that when it's open, it stops the motor from moving. Over here, we've got our reverse push button, which is just like the forward. Okay, then we've got the contactor. So let's circle this whole thing here. So there we go. We've got a normally open contactor. Now that is going to close when the motor is running. Okay, so that's going to close sometime after we command the motor to run, right? The person pushes the forward push button to close it, and it takes some time for that motor to ramp up and start running, and then that forward contactor will close. Similarly, we have one for the reverse direction. Okay, and lastly, we've got this right here, which is the overload, normally closed overload input to the PLC. So this is going to open whenever there's an overload. So that's a bad thing. You want to stop the motor when you have an overload so it doesn't damage your motor. Okay, so those are our inputs. Now I'm going to change to a different line color here. I'll go with blue, and I'm going to circle the outputs of the PLC. So here we've got M1, which is, I think it's probably like a magnetic relay or something like that, that will close all of these here, and it'll connect the power to the motor. Now notice this. So when we're going forward, the L1, L2, L3 connect directly to T1, T2, and T3. All right. Now our next output is right here, labeled as M2. So I'm going to assume this is another magnetic relay of some sort, and it's going to close these contacts. So if you look closely here, how this will work now is, because these ones will be open, we're taking line 1, and line 1 ends up connecting to T3. So we're reversing, or we're switching line 1 to T3 now. Line 2, if we follow the wire, it goes from line 2, L2, all the way to T2. So no difference there between forward and reverse. And then right here, L3 comes over and it ends up connecting to T1. So there you can see the difference between commanding the motor to go forward and reverse. We're essentially flipping the connections to T1 and T3, and that'll get you the different directions on the motor. All right, so there it is. That is everything, all the I/O points that I can see, I think, on this diagram. So let's go back to the PLC. All right, so I've got my inputs for the 3 push buttons. Now another thing I've done here is, this is a convention that we used when I was working at General Electric, is that for all inputs, we prefixed the variable with an I underscore, just so it was perfectly clear that this is a physical field input. And for outputs, we used an O. And I put M in front of these because we're used to calling them M bits, but these are essentially M bits. They're internal memory. They don't connect directly to any I/O point. All right, so back to what I was saying. So there's my 3 push buttons. Here's my 2 contactors, and there's my overload input. Okay. Next, here's my 2 outputs. I'm calling this the forward motor command and a reverse motor command. Okay, now I've got 3 more outputs here because that was part of what the assignment 2 instruction said, was to create 3 operator indicator lights that indicated whether the motor was moving forward, moving reverse, or there was an overload detected. Okay, the next 2 M bits, we could call them, are the start pulses. The instructions said that we need to provide a 3-second start pulse to the motor to give it time to start running for the contactor to close. Okay, so that's all of our I/O points. Now the other thing I'd like to just point out here is how I've done the comments. Now this is another standard thing that I did, that we did as a team when I was working at General Electric, is we would, in the comments, indicate what the on or true state of the I/O point indicates. So the reason we like to do this is to avoid ambiguity. For example, if I just put a comment beside this stop PB that said stop push button, well, that's still kind of ambiguous to someone else that might inherit my program as to what that means. Does that mean that when the push button is open, it's stopped, or when it's closed, it's stopped? So if we put something like this, that removes the ambiguity. Although, in most cases, if I just said stop push button normally closed, you'd probably be able to figure it out. But anyway, this is how we did it. So this is how I'm used to doing it. And this is my preference, because it just makes it completely clear to everybody exactly how this is, each I/O point is working. Okay, so we've created those I/O points to begin. The next thing that you're going to want to do is create a function block for the motor control. So here's my function block, and all of the ladder logic is given to you in the lab instructions. It looks exactly like this. I just screenshotted this. Okay, so the first thing we have here is our pulse generator. Now, many of you might have used a TP block in your assignment 2, a time pulse block, to generate this pulse, and that's fine. That'll work. But if you look over here, you'll notice there's no TP block. And that's common. Really, the only one of these timers that is supported by every PLC I've ever seen is this TON. And it's really all you need. You can use a TON to generate a pulse. You can use a TON to generate something equivalent to a TOF. In this case, we've got both, but there's no TP. So I had to use a TON. So that's what I've done here. So how this is going to work is, when the stop push button is closed, and then the forward push button gets closed, we will start the pulse. All right, and This Q bit here is the output of this timer. So the time, this will initially be off. So this normally closed contact. So we'll have power going right across, and this will stay on. All right, now this being on, we'll start off the timer. Now when the timer hits 3 seconds, the Q will turn on, which will then open this up, which will then kill the pulse. All right, now we need to latch around the forward push button because it is momentary and the user's not going to hold their finger there for 3 seconds. Well, I guess they might, but they probably won't. All right, so this will, in the end, generate a 3-second pulse. Okay, we're going to use that 3-second pulse as our start pulse for the motor. Now we need that because it takes a while for the motor contactor to close. Right, the motor contactor is right here, and we're going to use that to latch the motor running. So the idea would be like this. Again, the stop push button is closed. We don't have an overload, so the overload will also be closed here. And then finally, we want to have an interlock that prevents us from moving forward in the event that we're already trying to go in reverse. So that is sort of duplicating the mechanical interlock that was shown on the diagram. Okay, so we've got power running along here. The pulse comes on for 3 seconds and it stays on for 3 seconds. And sometime within that 3 seconds, this contactor has to close for it to then stay on through this power path. All right, reverse is pretty much exactly the same. It's just duplicated logic for reverse and using all the reverse I/O points. All right, and lastly, I've got some logic here for the motor running lights. That's pretty straightforward. If the contactor is closed, the light comes on. One thing I'll note here, and I did this above, is how I've kind of branched this. Now, I don't love this. I'd prefer to have this wire connecting directly to the left power rail, but for whatever reason, TwinCAT 3 doesn't allow any more than one power rail connection in a network. And so I kind of thought, well, I could use another network, but what I'd really like to do is group all the related logic under one common comment. And so in the end, I opted to do this branching. You may prefer to just put this one in a second network. It's really up to you. It'll work either way. Okay, lastly, we have our overload light that when a overload is detected, we turn on the light. And that's it. That's the control logic. That's the main solution to assignment 2 right there. Same goes for this here. I'd rather have that connected directly to the power rail, but again, the same limitation has driven me to do this kind of weird looking branch that is whatever. I'm living with it. Okay, so that's the first part. After you've implemented that, you might want to then build your application, activate the configuration here just to see if it runs, if you've made any mistakes. It's always a good idea to build after you've created a little bit, because don't wait until you get to the very end, because if you wait to the end, if you have a mistake, then it could be anywhere in that entire program. If you build now and it doesn't work, at least we know it's in this function block somewhere, or it probably is. That's probably where the problem is. If I wait till the end, well, heck, I don't know where it is. Okay, after you've created that, you're going to want to add it to your main program. So again, create the instance of the motor control function block and type it in here. Now at this point, you won't have motor simulation. Okay, build it, run it, see if it works. All right, so I said you should build it after you create the function block, but really you should do the building after you've added it to main, because if you don't add it to main, it won't run anyway and you won't be able to test it. So add this first. Okay, the next part of the lab is something a little bit new, but it's just really more of the same. It's just the concept is new. So the idea here is the motor simulation. So before we get there, let's go back to this. So looking at this logic here, we can see that we're latching the motor running based on the contactor closing. So this logic here is highly dependent upon the field equipment, in this case the contactor, closing within 3 seconds of us telling the motor to run. Now, because we don't have a physical motor, it's not going to close. So we'll say go, and this pulse will go on for 3 seconds, and then it'll end, and then the motor will stop. Right? So that is a fairly common problem that you run into as a PLC programmer. You're making a PLC program to control some field equipment that doesn't exist. And this, this has happened pretty much, I think, every program I've ever written. Either the equipment doesn't exist, or it's unavailable for me to use for testing. So, I used to work in the nuclear industry, and we would write a PLC application to control, usually to replace some legacy system in the plant. Now, the power plant can't just take that equipment out and send it over to General Electric and have me test my system on it. And they also don't want me to take my untested PLC control program and carry it over to the power plant and then just plug it in and see if it works, right? This is a nuclear power plant. It's got to work the first time. Sometimes also project schedules, if you're making a new system, they want you to develop the PLC application concurrently with the people that are making the electrical and mechanical system to go along with it. So again, you don't have equipment to test with. All right, so there's a few solutions to this. Most commonly in the past, what we would do is we would create a simulation using like a software-based simulation using something like LabVIEW, or there's some other tools. We used one called Pix Pro a few times, which LabVIEW is a bit nicer, but some other external system that you could create a simulation of the field equipment, and then you could connect that to your PLC, so you could test your PLC before you had any of the field equipment available. Now, we can't really do that because it would be too complicated, and we don't have LabVIEW, we don't have all this stuff. But what we can do is we can build a simulation right within our PLC application itself that will drive this value. So it's going to close the contactors as we would expect that the field would do. And it will also allow us to inject overload faults. So this here is always going to be open. All right, and if we want to inject a fault, it's always going to be, it'll be normally closed, and we want to be able to inject a fault by opening it. Now, we could simulate that by just writing a value to it. But there are situations in real life, like I'm thinking of the nuclear power industry, where you want to be able to test how your PLC application reacts to abnormal situations. And maybe you don't want to simulate, or not simulate, you don't want to create those abnormal situations in the real equipment, because you might create an unsafe situation. You might have to make some modifications, like breaking wires and things like that you don't want to have to fix afterwards. You might also be just breaking or damaging equipment in creating these abnormal situations. So another benefit of the simulation is that you can simulate abnormal conditions without having to break anything or do anything that's dangerous. Okay, so I probably talked too much about that. So let's get to the simulation. So the simulation is going to be pretty simple. We really only have to simulate 3 signals: our forward contactor, our reverse contactor closing, and then the overload. Okay, so pretty simple simulation here. I'm going to say when we get the forward command to the motor, and I've put in an interlock here that's probably not strictly necessary, but when we get a forward command, after some amount of time that's defined by this global variable here, which, by the way, let's go back a step. We have to create these ones as well. So these are the next 2 variables to put in here. And I've prefixed them with the word sim, just so we know that they are part of the simulation. So these would be deleted later on as well when we put this system into commissioning. And that's the other reason why I'm putting this in a function block is, if I was going to put this into a real control system, I would delete this function block because I don't want to simulate the field when it's running for real. Okay, so back to what I was saying. So we're going to close this contactor some amount of time after we command the motor to run. Now, I want to be able to adjust this amount of time, and so we're going to use an HMI control to adjust that. Now, ideally, I would have been able to create this as a time variable, but you can see back here that I had to make it as an integer right here because there weren't any controls I could find on the HMI that would allow me to connect a time variable to it. So anyway, that's why I've made this an integer, and then I've put this conversion block. So here is one of the first new things that we're doing in this test. All right, so I apologize for having a new thing in a test, but this is easy, and I'm going to show you exactly how to do it. Okay, so I'm going to delete it just so I can recreate it. Okay, let's delete that too. Okay, so how do I create this? So over here, I can just right-click. There we go. That's weird. So you got to right-click on the line, not on the box beside it. And I'm just going to choose Insert Empty Box. Okay, now I need to now click on these question marks inside, not the ones on top. It's got to be the ones inside the box. And I'm going to type int to time. All right, and then I hit enter. Bam, that's all I had to do. Okay, now I want to put that same variable back, so I'm just going to take it here. I'm going to hit Control-C to copy, Control-V to paste it. All right, so that's how you can create that. Hopefully that still feels fair on a test, all right? Pretty straightforward, I hope. Okay, so implement this logic as is, as shown. And now we've got a simulation where we can run our imaginary motor and see how it's going to react. We can now inject faults by using this variable here to inject an overload fault to see how our control logic is going to react. We can vary this time to see, well, what happens if the contactor doesn't close? That's what pick up means, is that it closes. If the contactor doesn't pick up within the 3-second pulse, what happens? Or what if it picks up after half a second? What if it picks up after 4 seconds? How is it going to react? So that's the goal behind this simulation logic here. Now, you're also going to, I'm going to save it. You also are going to have to add this function block to main. So that's what's here. So I created an instance of it right here, and then I added another call to a function block here. So this is ultimately what your main should look like. All right. If at some point you accidentally click this and look at this, this is just a structured text representation of what's being shown in the table. If you see it though, I'd hesitate to edit it that way because you might make a mistake. I've also seen some students that have accidentally taken these and put them up here. Now that isn't going to work. So don't do that. Make sure that these are down in this part, and the variables, let's try to keep it on the tabular view and just edit it that way. All right. So there's your PLC control application. At this point, you could run it and see that it works and make sure there's no bugs. Again, if you find a bug at this point, assuming you ran it when you created the motor control, the new bug has to be related to what you just changed in the simulation. So the bug must be here somewhere. If you make sure yours looks exactly like this, it'll work like a dream. Okay, last step is going to be to create the HMI visualization. All right, so here it is. This is what I've come up with. All right, now there's a couple controls here that we haven't used before. One of them, where is it here? One of them is called a group box. So these things here that I've put around here, these are called group boxes. They don't have any function other than to group related controls. I've put them here for clarity to try to make the HMI look more understandable to everybody. You can omit them from yours if you want, or you can include them, but it's really not rocket science using them. All right, so if I wanted to use it, I just go to my toolbox, I drag over a group box. All right, and now there's a little box up here that you have to click to drag and move it around. I can resize it. Oops. I can resize it any way I want. Anything that I wanted to put in it, I could just, for example, let's grab a lamp. I just drag it in. Now it's in the box. And when they're in the box, one of the cool things about being in the box is if you choose the box, see how it moves with the box? So that is kind of handy for getting sort of bits of your visualization arranged and organized, and then you can kind of drag it where you want it. And you're not like dragging individual things around. All right, giving it a name up here is pretty straightforward too. You just go up to the text field and type something in. You know, this is my cool stuff. Goes here. Whoops, that's not how you spell cool. All right, cool stuff. All right, and there it is. There's my cool stuff. The other thing I did here, and again, this is just sort of gravy, is I changed the font so it looked a bit bigger and bolder. So I just went to the font here and I double clicked, did one of these, and I chose bold and I set the size to 12, and then I said okay, and there it is, bigger and darker. Okay, whatever, include these, don't include them, it's totally your call. Okay, the next new control we haven't really covered is this one here. Now this is called a slider. And you can see here all the settings that I chose to make mine. I kind of played around with these scale numbers a little bit to try to make something that looked reasonable. But what we're going to use this slider for is for adjusting the contactor pickup time. So we can test, well, what happens when it's less than 3 seconds? What happens when it's greater than 3 seconds? How does the motor control react? All right, so to do this, to get one of these sliders, again, go to the toolbox. Down here under Common Controls, you'll find a slider. Drag it on your screen, and here I'm going to put it inside my box here. And let's just drag this over a bit. Oops. And let's make this bigger. Okay, now I want to make the slider a bit bigger, so I can just make it a bit bigger. You can play around with these things. So here, you see it's not showing any numbers. So I want it to show a scale. I just click that. Now I've got a scale. Now I want this to go, in my case, I did 1 second to 4 second, but we're in milliseconds, so that's 1,000 seconds to 4,000. So I just went in here and I said 1,000, and scale end, I said 4,000. All right, now it kind of looks crazy because we have our main scale set to 10. So let's change that to say 500. All right, so now it's only going to show me in increments of 500. All right, the subscale, as far as I can tell, I don't know, it doesn't show up. So I don't know what this is, but just leave it. Maybe you can figure out how to show it, how to make it show up. But I gave up. I don't care. This is good enough for our purposes. All right, and then let's just look back to the one I already did. We assigned this simulator contactor pickup time as the variable. All right. That's it. Okay. Other than that, dragging all of this stuff and assigning variables to it is exactly the same as what we've done on previous labs. All right. So I don't want this cool stuff box, so I'm just going to select it and delete it, and that'll wipe out everything. Okay. Now let's see at how this is supposed to work. So I'm going to, I think I've already got it built. So I'm going to go online. Okay, so I've made a change. Oh yeah, because I've kind of been dorking around with stuff. So I'll choose, I'm going to log in with online changes. And, oh, you know what? I'm glad this came up. Anytime this says that you may have unintended consequences, do you want to continue? I go with no. Let's not do that, because I don't really know what it's getting at. So I'm going to say no. And one time when I did it, everything kind of went funky. So instead of just logging in again, I'm going to do an activate configuration, which will rebuild everything from scratch and load it into the simulated PLC. So we'll wait for that. Now, whenever this is happening, you should always be looking in this error window that shows up at the bottom. If you have an error, oh my goodness, and I do have an error. I wonder what that is. Well, this is unexpected. I didn't think I made any changes that would cause an error. Oh, and the error went away. Okay. I'll take that as a win. But if you have an error, down here is where it's going to tell you what's wrong. And often you can double click on it and see what it is. But thank goodness I don't have any errors. So I'm just going to close that up because I don't really care about it right now. Okay, so now I'm all built. I'm going to click login to get into the PLC so I can work with this. Okay, now this button here should be a maintained button. So I want to click it to close the stop. So that's saying go. Motors can go. All right, I've got my contactor pickup time has a default value of 2000, so that's 2 seconds. So that tells me that that 3 second start pulse should probably be enough. So when I click a forward go, what we should see is the pulse should come on for 3 seconds. All right, the command, so this is my command to the motor, my output from the PLC to the motor should turn on. And then within that 2 second, or after exactly 2 seconds, the contactor should close, which would mean that the command will latch on. All right, and the motor will keep running. And at the same time the contactor closes, we should see the motor start running forward. Okay, so let's try that and see what happens. All right, there's my pulse, my command, 2 seconds later. Yeah, okay, so notice the pulse went away after 3 seconds. But the motor command continued because we want to keep telling the motor to go. And as long as we're still telling the motor to go, the contactor remains closed. And the contactor and the motor running are basically exactly the same signal because the latter was just if this one's on, then this one's on. All right, or if this one's closed, then this light is on. Okay, now I can stop the motor and everything stops. All right, reverse should work the same way. 1, 2, 3, signal goes off, motor remains running. Okay, hopefully these lights are helping you understand how this motor reacts, right? So we tell the motor to go, sometime later the contactor closes. Now let's try something different. All right, let's stop this and I'll close that again. Okay, now let's change the contactor pickup time to something greater than 3 seconds. All right, so now when I say go, we'll get our 1, 2, 3 seconds. Contactor didn't close within that 3 seconds. So that means there must be something wrong with the hardware. We were totally expecting the motor to start running within that 3 seconds, and therefore the contactor should close. Didn't happen, right? Because we've changed our simulation to keep the contactor open for 3.5 seconds. All right. Let's suppose it's a bit faster. So within 1.2 seconds here. So I'm going to say go. And notice, boom, the contactor closes even quicker. The start pulse remains on for 3 seconds regardless, but the contactor closes fast enough that we can continue running the motor. All right, next, let's try injecting an overload fault. Because what we want our motor to do, our control logic to do is stop trying to run the motor if there's an overload. So let's inject the fault, boom, and look at that. Motor stops running, overload light comes on. Awesome. Let's say I try to do it again. Can I run the motor if there's an overload? Nope. Can I go reverse? No, can't go reverse. All right. So as long as there's an overload, we're not going to be able to run the motor. The pulse is still being generated, but whatever. That's an internal signal of the PLC. Okay. So let's take that off. Right. So that now has given us the ability to really visualize how this is working. All right. Now, another thing I'm going to show you here, I'm just going to walk through everything here to show you what my settings are for all of these, or property settings are for every control. All right. So I'm just going to click through everything. You can pause the video at any point that you want to, if you want to take a closer look. I got to go offline first. So first, let's go offline, or log out rather. Okay, and now let's start looking at things. So there's my forward push button. Okay, notable things here are that it is connected to that input and that it's an image tapper because I want it to be momentary. Okay, reverse is similar. Image tapper connected to reverse. Stop is going to be an image toggler because it's a maintained button. I want to click it and have it stay. Okay, the lights. You know, I'm not going to be too picky about the color of these lights. Do whatever makes sense to you. I tried to pick colors that kind of seemed logical, but whatever color you want to use, go for it. Or maybe you can find a different indicator to use if you want to be creative. As long as there's some indicator that shows the state of all these things, that's cool with me. All right, let's look at this one now. All right, I'll just click through, hang there for a few seconds so you can see what it is. All right, so hopefully this has clarified at least somebody's understanding of how this motor control is supposed to work. If it's helped, I don't know. I'd love to let you know because I gotta say this lab took me a long time to kind of piece together and write out the instructions. So I hope it's been useful for you guys. All right, this guy. Here, I'll even click through all the labels so you can just see what I got. There's my box. Next one. Stop. All right. And the last one is this last box. Okay, so pause the video at any of those if you want to see exactly what settings I've used, but I think for the most part you'll be able to figure it out on your own. So that's it. That's all I got. I hope this was informative for you guys. It's been a pleasure being the lab instructor for most of you. I've enjoyed getting to know you guys, and I wish you guys the best of luck. So I'll see y'all in WebEx at some point as well, because remember, there is a demo component of this lab. Actually, let's just talk about that very briefly. Let's go to here, and let's go back to the lab instructions. All right, so down at the end. Okay, at the end of this this thing here, I talk about the lab report submission. You're going to note that it's a little bit different than the last few labs. I am asking this time for the main program. I probably should have asked for that for labs 8 and 9 to be consistent with what we're used to, because that's essentially what we would be calling the main organization block in Siemens world, and we put that in the labs. All right, so your 2 function blocks and your HMI visualization. All right, that's what I want to see in the lab report. All right, the demo. All right, I'd like you guys to join the WebEx meeting during week 15, so sometime here. Now, I want you to join your lab period. Reason being is if you don't, I'm going to have every student show up on Friday morning and want to do their lab, and then we'll have a giant queue of people waiting to do their demonstration. The demo should be pretty quick. I just want to see briefly show me the ladder logic and briefly show me the your visualization functioning. So when you get to the when you get there, I'd be happy if you had it all built and running and ready to go. All right. And lastly, the other thing worth looking at here is further down, I've put in the rubric that I'm going to be using to grade you on this lab test. So I'm doing 50-50 marks. Half the marks are going to come from the demo that you show me, and I'm basically just going to check does it function correctly. And so I've given you all the ladders, I've given you everything you need to know. So this really should be a no-brainer for most people. It should it's going to take you some time to implement it, and there may be some debugging and you might hit problems, but all the information is there. So I'm hoping this goes well. All right, and then I'm going to look at your lab report, and here's all the stuff I'm going to look for. right? Did you give some good variable names? Did you give a comment? Now, again, I've already given you good names to use. I've already given you comments, so this should be pretty simple. Do you have a main program that calls both function blocks? Did you create both function blocks? Did you put comments in each network? Did you give all your timers a good name, or did you name it something like poor, like timer 1, timer 2, right? That's a bad name. Describe what the timer is used for. And lastly, did you organize the ladders in a fairly reasonable, logical way? Again, do it the same way I did it. I think that's logical. All right. And lastly, the HMI visualization. All right. So I would like you to make it look pretty good. Mine looks okay. Maybe you can come up with something that looks even better if you want. At some point, I considered using like real pictures of motors to show the motor running, but in the end, I thought it's too complicated. But maybe you can do that and impress the heck out of me. So yeah, I'd like to see that everything's there. So all the indicators, all the buttons, and that it's been arranged fairly neatly. Like use some of those tools I showed you to kind of align things. It doesn't have to be totally perfect, but like make it so it doesn't look like crap, and put a label on everything so that I know what each light is. I know what each button does. All right. So right there's how you're being assessed. There should be no reason why everybody in the class shouldn't be able to get 100% on this test, and that'll bolster your mark. So keep this rubric in mind when you are putting your lab report together. Anyway, that's it for now. Farewell, and good luck.